Good morning to everyone. Very good morning. Today, we would like to concentrate on binary search. So, previously, we have discussed what is divide and conquer and how divide and conquer has been implemented while any kind of application or problem statement will be given to you. And today, the first application for divide and conquer is binary search. How binary search will be gets operated, and what is the premises? Otherwise, what is the principle of binary search? While the binary search will be operated or evaluated by using divide and conquer application. Let us have a look here. Let us discuss about this particular point today, and this binary switch will be continued for tomorrow also probably. I don't know whether the time will be permit me or not to discuss with you. So today, I don't know. So it could be taken at least two or maximum of three classes. However, we would like to start our work without any further delay. So here, binary search. What is the actual problem of binary search here? So actual problem of binary search will be seen in such a way. So you have given a particular problem A of P, so sorry, A of I, where I will be less than or equal to 1 will be less than or equal to I will be less than or equal to n. So that is why. So you have n number of elements will be there. Probably one element, probably two elements, probably three elements, and so on. N number of elements are there with you, and these n number of elements will be already in sorted order. I have given an assignment to you people that recursive algorithm, recursive implementation of binary set. Few of you people have used bubble sort. I don't know why you people have used bubble sort. So while discussing any binary search algorithm or binary search problem, we would like to consider the data is already in sorted order. Okay, the data is already in sorted order. When we'll go ahead with real-time application, real-time in the sense while it is being actually implemented in IT industry, then so sort followed by search operations will be binary search operation will be done in terms of actual implementations. But as far as learning point of view, we'd like to consider that the data which we have given is already in sorted order. So here, normally in algorithms, sorting or ascending order could not be spelled out. So this ascending order will be always specified as a non-descending order. Non-descending order in the sense it is opposite word of ascending order, so that the data will be already in ascending order only. So ascending order here in the sense how the data will be seems here in the sense. So A of 1 is less than or equal to A of 2 is less than or equal to A of 3 is less than or equal to, so and so on, less than or equal to A of n. This is the meaning of non-descending order. And then second point will be, point number 2 will be, consider the problem to determine whether an element, whatever the user wants to search, that particular element will be considered as X here, whether X is present within that particular list or not. So that is the second step which we have to take into consideration. First step is you have a list of elements in already sorted order. What is the order of sorting here in the sense? That is a non-descending order. Simply speaking, ascending order. Then second step will be, we would like to consider one more element. So that element will be X. You can name them, you can name it like anything, but I have taken here as X, which is present in the list or not. That is the second point. Third one is, in this particular second point, where exactly we have to take into consideration that if X is present within the list of elements, then we have to determine a value of J, another index that is J, another index that is J, such that A of J equal to X. In actual implementation, this J will be called as mid. J will be called as mid element. So we have to identify or we have to determine a value of mid in actual implementation. I'm algorithm implementation. So A of mid such that A of mid equal to X or not. Okay, if it is presented, then X is present in the sense this particular equality will be returns to. That is the meaning here. This particular equality will be returns to. Then if this particular case is not true, this case is intuitively not true here in the sense, then so if X is not present, if X is not present within the list, then J will be written as 0. Why it has been taken 0 here in the sense, our list has been started right away from 0 to n. Whereas if you implement the same kind of array implementation in terms of any C, C++, Java, something like that, index value of C, C++, Java will be starts with 0, and the final value will be so n minus 1. Thereby, so you have to return rather 0, you have to return minus 1 based on the structure of otherwise the storage structure of the particular program. Then you have to change the value, or the mid value will be J will be considered as mid. Mid value will be either it is 0 or it is minus 1. Okay, so don't consider that if J value will be equal to 0 in the sense if X is not present, if X is not present, you have to return. So you have to return so either 0 as far as algorithms are concerned, or minus 1 as far as languages are concerned. Okay, in this way, we would like to perform. Then, see, if the same problem, this is actual problem. Here it is, this is actual problem. This is actual problem. So what we are supposed to do? So we have a non-descending order list of elements are there with us. And within the non-descending order list of elements, we would like to identify, we would like to target for one particular element which is available with us or not, with that particular list or not. So to do that particular operation, we have two choices. If value target element, what we are trying to check that particular element is existed, then you have to return mid. You have to return J as per the algorithm, as per the program, it is mid. Whereas if this X is not present in the specific list, then we have to return 0 as far as algorithm, or as far as some kind of programming languages such as C, C++, Java, something like that, we will return minus 1. If minus 1 will be there, your targeted element is not existent. Other than minus 1 or other than 0, the targeted element will be existent in so and so location. This is our problem actually. This is the problem. And how this problem can be applied using, this problem can be solved using divide and conquer strategy or divide and conquer approach. How this can be. Look at this. So let you have to consider in divide and conquer what we are trying to specify. So P will be considered. P is a problem. Here the problem is so binary search. Here the problem is binary search. So this binary search might be having some kind of element, something like this. So n total number of elements, A of I2, A of m. So these are the elements where I will be equal to probably that is 1 or 2, 3, and so on. So where m equal to n, number of elements will be m. So m equal to n, and the element to be searched. Element to be searched here. So this is the list of elements which we have with us, and this is the size of your list, and this is the element to be searched within the list. This is the problem actually. And of course, I have given the complete information only. N is number of elements within the list, and so A of I2, A of n will be A of m will be list of elements, and X will be the element to be searched. Okay, this is the specification. Within this particular thing, of course, we'd like to always consider this is in already in sorted order, which is a non-descending order. Whatever I have specified within the actual problem that has been given here. So within this particular specification, what exactly divide and conquer strategy can be gets applied here? How this can be gets applied here? Look at this. So we have two cases. Case number one will be, so if problem is very small enough. So here already in the previous class I have given binary search and quick sort and merge sort will be merge sort and identification of maximum minimum of elements will be always taken. So one, whereas in Stressen's matrix multiplication defective chessboard problem, these two will be taken 2 by 2 as so the minimum value. So here we are trying to evaluate a binary search. Since it is a binary search, if n will be equal to 1, then small of p will be returns true. Small of p will be returns true. Only one element is there with you. Single element is there with you. Then your small of p will be get satisfied, so that so the search might be successful or the search might be unsuccessful. Let us see. In this case, small of p will be take the value of I, and here x equal to a of I. X in the sense the element which is being set by you, that is actually equal to a of I. Then so whatever the index value of I, that can be sent to the user. So within that particular location, with that particular location, the particular value has been identified. Otherwise, it will be taken as 0. Of course, as far as algorithms, it could be considered as 0. In other languages such as C, C++, and Java, it could be -1. Okay. So this is the first case. Maybe search may be successful or search may not be successful. How this will be calculated here in the sense, if x will be the single element, the targeted element will be the existed element of the list, then search is successful. Otherwise, search is unsuccessful. So that is the binary search algorithm will be returns 0 or -1 based on the language. Now, so if P does have more elements, more than one element, then the problem will be divided into several number of subproblems. Okay, several number of subproblems will be taken into consideration. How this could be done? How this could be done? Let us take this. So we have to take one particular index, that is Q. So here, what do you mean by Q here? Q is the mid element as far as actual implementation. So from I to M. So you have to operate some kind of operation to identify the value of Q here. So normally in programming languages, how this could be done here in the sense. So I plus so M divided by 2, as far as divide and conquer. Always it could be divided by 2 so that it could be taken. So this value could be so Q here. Okay, and compare X value with A of Q. X value with A of Q. Otherwise, in our program, what we have written, so A of mid equal to X or X equal to A of mid or not. If this could be the case, then your problem will be get solved. There is no further proceeding to be done, because already whatever the actual output or ultimate output you are required, that output is already acquired. The search is successful. So therefore, you are not supposed to go for further. If it is not the case, I mean, A of X is not equal to A of Q, then second case will be whether X will be less than A of Q. If it is true, then X can be searched within this particular sublist. Within this particular sublist here, A of I, A of I in the sense previously we have taken, so I to M. Already I have given some information. I to M. So A of I plus 1, and so on, A of Q minus 1. Because already we have a Q is calculated something like this as far as a programming point of view. But here there is no proper proper equation to identify Q here. So I have given as far as the program is concerned here. So Q will be identified. Then obviously we'd like to consider, so A of 1 to A of Q minus 1, this is the sublist. A of so Q plus 1 to A of M cannot be taken into consideration, that will be eliminated. So I have given clear information in further forthcoming slides, so you have to get a clear idea about that. Okay, then if it is this is the case, this case will be gets true. Obviously, you have to search within this particular list of elements. then how this could be done here in the sense problem will be reduced to your actual P will be reduced to Q minus I, Q minus I number of elements. For example, so 1 to, so 20 elements are there. So here 21 divided by 2, that is 10. So 10, yeah, 10 equal to your value or not? No, it is not the specific value because in B's case, we'd like to set that yeah, mid element is not. So this condition is gets false, so that we'd like to come here. So Q minus I in the sense, so Q minus I will be taken something like this 10 minus 1, that is 1 to so 9 values. Okay, 1 to 9, sorry, n value can be taken, n value can be taken as so 9. So totally 20 elements are there. You have eliminated approximately 11 elements from the set, and then a of I to a of Q minus 1. Then what is the element you are trying to set? Okay, what is the element you are trying to set over there? So that could be taken into consideration. Q minus I in the sense, so Q equal to 10, I equal to 1. So therefore, the number of elements to be considered for second round or second recursive call or second iterative call will be 9. Okay, that is the meaning here. Then, if this is not the case, for example, this is also, so this is also not false. Yeah. So this is also not false, or not true. Sorry, not true. This is also false, and this is also false. Both will become false. Then we'll come across with this. If x is greater than, if x will be greater than what do you call a of q, then again x will be set within the sublist. The sublist will be a of q plus 1 to, I mean a of mid plus 1 to, so a of n, something like that in terms of actual implementation. Here we have like to take a of q plus 1 to a of n. Okay, therefore the problem will be reduced to, so m minus q. So m will be maximum elements, that is actually previously we have discussed with the 20 elements. So 20 minus, so q is 10 actually. So remaining 10 elements are going to be taken into consideration. So right side, the remaining 10 elements are going to be considered, and they're supposed to be gets operated as your problem space for binary search. Okay. So these are the three cases where exactly we have to consider while operating this binary search here. So this binary search will be, okay, already have given, already told you. So Q will be considered as so mid in programming languages. Q will be considered as mid in programming languages, already have given. So right away from the beginning, I'm specifying that Q is also called as mid, something like that. So based on this one, how you can implement the problem here is, this is the way to implement the problem here. So then you could see. So element to be searched. So before going to give the algorithms, let us examine the search space, how the search space will be reduced from this particular given list of elements using binary search with the what do you call divide and conquer strategy. So let us consider these are the elements 10, 20, 30, and so on up to 130. Totally indices values will be 1, 2, 3, 4, 5, 6, and so on. So 30. Now let us consider like to search for 20. We'd like to search for 20 here. 20 is available with the index value as 2 here. So how this could be done? So I'll give in some kind of animation here. You could see. So that is the first element, and this is the last element. So this is I, and this is M. First is implicitly called as I, and last is implicitly called as M. So here at this particular point, the first will be equal to 1, and at this particular point, the first will be equal to, so 30, 1, 3, 30. Okay. Now, we'd like to calculate, so mid value, mid operation. So as far as C, so integer by integer equal to always integer, there is no problem. So in C, there is no problem. But some kind of languages, even you have given integer divided by integer, will leads you to get the float value. So that is why we have taken, so float. This is the algorithmic representation for floor. The floor will be represented something like this. Within these two, if you write any kind of expression, that expression will be taken as floor. So floor in the sense, for example, 2.5 will be there with you. Floor value for 2.5 will be 2. Okay. Floor value for some 13 point, some 25 will be equal to 13. Okay. Floor is always gives you the integer, so least integer which is being taken by the expression. Okay, that is called as a floor value. So based on this one, after identification of this one, so first equal to 1 plus the last equal to 13, okay, divided by 2, divided by 2, that will be equal to 7. That is 14 divided by 2, that is, of course, this is floor value actually. So 14 divided by 2, that is 7. So therefore, the value will be equal to 7. So here, we'd like to identify the mid. First is this one, last is this one, and mid is here. So first will be equal to 1. So last will be equal to 13 so far, and then mid value equal to 7 so far. Okay. Then what is the next operation which we have to take? Whether a of mid equal to x or not. Okay. So that is going to be checked here. Thus a of mid is equal to element. The required element, that is element to be searched will be 20. 20 is equal to 70. No, it is false. Therefore, we like to go for in algorithm. We like to go for second operation. That is a of mid is so greater than or less than. So element is less than a of mid. So that is 20 is less than, so 70. Yes, it is. Yes, this could be true. Since it is true, so how this could be evaluated? Let us go ahead with the explanation. And so the problem will be reduced first to mid minus 1. First to mid minus 1. First to mid minus 1, first value is so 1, mid minus 1 value will be 6. So now I'd like to consider 1 to 6 indices values as our problem space, and so whatever the elements which are available at this particular mid plus 1 to last, so they will be eliminated from our problem space. Let me show you this one using animation in the next slide. Okay, then. So here mid equal to first plus last divided by 2. So first plus last divided by 2 in the sense, so 1 plus mid minus 1. Mid minus 1 will be 6. So that is 6 plus 1. So that is 7. 7 by 2, which is floor value. So 7 by 2 will be equal to 3. Mid value right now is 3. So therefore, your elements will be seen in such a way. Okay. Okay. In such a way. So here it is equal to 1. Here it is equal to 3. And here it is equal to 6. Now, so already one comparison was happened with 70. Already one comparison was happened with 70. So that could be there in the actual binary search and remaining. So because of so satisfaction of the condition, element is less than of a of mid in the first step. That way we have checked out. So yes, it is true. So that is why we like to consider. I have drawn something wrong here. Okay, one moment. Wait for a while. One moment, please. So this could be drawn right away from here to here. I'm sorry. Okay. So something like this, it could be taken. So 8 to 13, these list of elements will be eliminated. Our problem space will be reduced right away from 1 to 6. And right side, so problem space will be not considered. Just underline this particular line, not considered. Okay. So therefore, this problem space will be eliminated from our from our where it is. So because I have taken so white as the pen color, so that is unable to identify. So look at this. This particular space is not supposed to be taken into consideration. This is eliminated. Now, follow the same kind of step one more time. Here we have first is there with us, so last is there with us, and mid also be there. Now we'd like to search for whether so a of mid is equal to element or not. No, that is so a of mid is 30, 30 equal to 20. No, because it is false. And we'll go ahead with the element is less than, so A of mid, that is 20 is less than 30, yes, it is true. Because of true, so again, the problem space will be again reduced. Now, first will be equal to 1, whereas mid minus 1, that is equal to 2. Okay, mid minus 1 in the sense mid is already equal to 3, minus 1, that is equal to 2. The problem space will be again reduced. Now, look at this. So again, we'd like to identify the same kind of process one more time. That is mid equal to first plus last by 2. So here first equal to 1 plus last in the sense mid minus 1. That is so 2 divided by 2. So which is under floor value 1 plus 3, 1 plus 2 in the sense 3, 3 divided by 2 in the sense actually it is 1.5, but it is not considered as 1.5. So I'm sorry, there is problem. Let us wait for a minute. Yeah, so correct only. So what we considered as correct only. So here it is 1 plus 3, 1 plus 2, that is 3 divided by 2, that is equal to 1 here. Why it has been taken as a 2 here? Okay, however, let me consider. So let me consider this is not. This is 1 here. 1 here. Okay, however. Now, so already this space is already eliminated. Now this space is already eliminated. This space is already eliminated. Now, so mid will be pointed here. Actually, this is mid. Actually, this is mid here. This is actually mid here. Sorry for this one. So within this particular mid, we'd like to identify does mid element equal to element or not. So actually, this is actually false. So I have made while preparing this particular thing. So I have made some problem. Okay. However, actually problem is not successful. I have considered here this is 3 actually. This is 3. For example, this is 3. Everything explanation is good. So every explanation will be good. So let us see. If that is 3, so I have given in the further slides. I have given very clear information. So very clear information, very clearly. So in future, I'd like to take care without having any problems here or questions here. So 4 by 2, that is actually equal to 2. So therefore it could be 2. So I have taken this in such a way. The problem will be again reduced by some more. The problem will be eliminated somewhere here. So therefore F mid will be equal to element as it is. As it is here. Then your problem will be get succeeded solved. Okay. So this problem is there. So I have while writing. So probably this was prepared in late night. That is 12:30 or 11, 12:30 or 1. So that is some small mistake has happened. So in future slides there is no mistake. Everything is correct. Okay. Let us take this. So in this way you could identify. So you could identify whether so-called bind research will be done or not. Then what are the algorithms? Algorithms will be, these are the algorithms. Bind research using iterative method. Bind research using iterative method. Okay, how this could be done. So the parameters for bind research for iterative method is list of elements, number of elements, and then element to be searched, size of your list, and element to be searched. Now here low equal to 1, high equal to. So actually in C++ we'd like to consider that the low will be equal to, so always taken as 0 because array index value could be taken as 0 so that it was 0, and the high will be taken as n minus 1. 0 to n minus 1 elements in languages. But in algorithms, we'd like to start our work with 1 onwards, 1 to n. Then we'd like to identify whether low is less than or equal to high or not. If it is true, 1 is less than or equal to n, yes it is true, 10 will be equal to 20 for example, yes it is true, then we'd like to identify mid with the same formula, there is no change in formula. Okay, after that, if a of x is less than mid, then so high equal to mid minus. A of x is less than mid, so I equal to mid minus. Otherwise, A of x is greater than mid, then low equal to mid plus 1. Then followed by, if these two are not true, obviously we'd like to consider, we'd like to, yes, go ahead with these two are not true in the sense f mid equal to the element. So therefore we have to return whatever the value of mid here, that is going to be returned. So therefore the problem will be get solved. The problem will be get solved. In this way, you like so. If continuously either this one or this one is getting true, for example, continuously this one or this one are written true, obviously never it will be goes to this particular area. Never this will be goes to this particular area. So therefore, finally you could return 0. Of course, as I told you in the previous slides also, either it can be returns 0 or it is returns minus 1. Minus 1 in the sense as far as implementation point of view, 0 in the sense algorithm point of view. Okay. In this way, you could. Then, in terms of doing the same kind of operation in terms of recursion, please look into this particular matter very clearly, very carefully, because many people have written some problem. So what you call some kind of okay. So list of elements and low element, maximum element, and then whatever the element you are trying to search. List of elements is A, and lower element, higher element, and then followed by maximum element to be searched within the given list. So here, if m equal to I, m equal to I in the sense this could be considered as small of p, small of p will be get satisfied. It could be written true because m equal to I in the sense only one element is gets existed in our problem. Then if this is the case, then obviously whether x will be equal to a of I or not. If x will be equal to a of I, this condition will be true. Whatever the value you have with you, I will be returned. Otherwise, it could be written 0. Otherwise, it could be written 0. If this is the case, will be true, then we'd like to consider as far as the divide and conquer point of view. So, the small of p will be the problem with the small of p will be getting. If this is not the case, if m not equal to 547, who is this guy? Okay, if it is not the case, then we'd like to consider. So mid will be, we'd like to take one element that is mid, which is taking same kind of operation. Then f I is, x equal to f mid or not. If this is the case, this will be true, then return mid value. Otherwise, if this is not the case, then we'll go ahead and check with x is less than f mid or x is greater than f mid. So if x is greater less than f mid, then bind which will be already we have taken here. The low value will be as it is because at left hand side the data will be available. So low value will be as it is, and the high value will be changed from what is that m to mid minus 1. Then followed by list of elements and followed by this one. So right side the list of elements will be eliminated. Otherwise, only left side data will be considered. Right side elements will be reduced. Okay. So then followed. If this is not the case, then mid plus 1. This is not the case in the sense x is greater than mid. X is greater than a of mid. So that case will be taken into consideration. So therefore, A and followed by mid plus 1 to maximum element followed by list. Here you could say if else part will be taken by you. So here else part will be taken by here. Then divide the problem. Divide the problem capital P into subproblems. Okay, SP. If you write SP here, you could have some kind of question. Then subproblems. Subproblems. Let me take sorry. Yeah, let me take SUB problems. Okay, in this way you can divide. So here, one thing you need to remember here, as far as divide and conquer, so conquer in the sense combine, conquer in the sense combine. So here, as far as the binary search is concerned, combine operation is eliminated. Combine operation is eliminated. Just we are trying to search. We are not supposed to do any other operation. We are trying to set within the given list of elements. That's all. So combined operations are eliminated. So that is why small of p will be checked here whether it is true or false. So we are going for checking this one. If it is returns false, then we'll go ahead for division. That's all. Division only for applying for division, and this division is being operated. Then during this particular division, so divide and will be gets operated. Conquer cannot be taken into consideration. Conquer is not there. Since conquer is not there, combine is not there, the complexity will be reduced. So this is the problem discussion today. So let me take the attendance because time is already gets over. Time is already gets over. So that is why let me take 18. Yeah. So I'll send out this one today. And if possible, people, if you are